For a long time, science has been built on a simple assumption: the universe follows rules. These rules may be complex, but they are consistent. They can be written down as equations, tested through experiments, and trusted to behave the same way today as they did billions of years ago. This belief is the reason modern civilization exists. It is why we can build satellites, predict eclipses, generate electricity, and explore space. Even when scientists disagree, they usually agree on one thing: reality itself is stable. But in recent years, that confidence has begun to weaken. Deep underground, beneath the border between France and Switzerland, researchers working at CERN have been collecting data that does not fully agree with our best understanding of how the universe works. At first, these inconsistencies appeared minor. The kind of small deviations that scientists expect when dealing with extremely complex experiments. Instruments are imperfect, measurements fluctuate, and background noise can affect results. So the data was checked again. The experiments were repeated. The machines were recalibrated. The calculations were refined. Yet the inconsistencies did not disappear. Instead, they became more consistent. That is when concern began to grow. In physics, small errors are normal. Persistent errors are not. When the same deviation appears across different experiments, different teams, and different conditions, it suggests that the problem is not with the equipment. It suggests that the underlying theory may be incomplete. This is what some physicists have cautiously referred to as a crack. Not a physical crack in space, and not a hole in the universe, but a fracture in the framework we use to describe reality. A point where our equations stop matching what nature is doing. Before we go further, if you are interested in deep explorations of the universe, fundamental physics, and the mysteries hidden beneath reality, consider subscribing to this channel. The content here is long-form, detailed, and focused on understanding the universe beyond headlines and surface-level explanations. What follows is not a quick story, but a serious exploration of one of the most important scientific moments of our time. Now, let's continue. CERN is not an institution that reacts quickly or emotionally. It is designed to move slowly, cautiously, and conservatively. Discoveries are not announced unless the confidence level is extremely high. Results are examined repeatedly, often for years, before being made public. So when scientists at CERN began noticing repeated anomalies, the reaction was not excitement. It was hesitation. Because anomalies are dangerous. An anomaly is not just an unexpected result. It is a warning sign that the rules may be incomplete. History shows that every major shift in physics began with anomalies that could not be explained away. The orbit of Mercury did not match Newton's predictions. Blackbody radiation defied classical physics. Atoms behaved in ways no existing theory could explain. Each time, the anomaly came first. The revolution followed. The situation at CERN feels similar. The troubling aspect is not one single experiment, but the accumulation of many results that all seem to point toward the same conclusion: our current model of particle physics may not fully describe reality. This model, known as the Standard Model, has been one of the most successful scientific frameworks ever created. It explains how fundamental particles interact, how forces operate, and how matter behaves at the smallest scales. Nearly every experiment conducted over the past several decades has confirmed its predictions with astonishing accuracy. And yet, the Standard Model was never considered complete. It does not explain gravity. It does not explain dark matter. It does not explain why the universe exists in its current form. For years, these gaps were accepted as limitations that future discoveries would eventually fill. What is different now is that experiments are beginning to expose these gaps directly, rather than merely pointing around them. This is what makes the current moment so unsettling. CERN was built to confirm theory. Instead, it may be revealing where theory breaks down. The discovery of the Higgs boson in 2012 marked a turning point. That achievement confirmed the final missing piece of the Standard Model. Many physicists expected that future experiments would neatly extend existing theories. Instead, what followed was confusion. As collision energies increased and measurements became more precise, unexpected behavior started to appear. Particles decayed in ways that were statistically unlikely. Certain symmetries appeared to be violated. Energy distributions showed subtle but persistent deviations. Each individual result could be dismissed. Together, they form a pattern. And patterns in physics are never accidental. The fear among scientists is not that reality is broken, but that our description of it is incomplete in a way we did not anticipate. That there may be deeper layers of physics operating beneath what we currently understand, layers that only become visible at extreme energies and conditions. This raises a fundamental question: what if the universe is not governed by a single, clean set of rules, but by overlapping systems that only appear consistent at certain scales? If that is true, then the reality we experience every day is only a simplified version of something far more complex. This is why the word crack is appropriate. Not because something has shattered, but because pressure is revealing weak points. Points where our assumptions no longer hold. And this pressure is increasing. As CERN continues to push the boundaries of energy and precision, these anomalies are becoming harder to ignore. The more deeply scientists look, the clearer it becomes that something is missing. To understand what that something might be, we need to understand CERN itself, how it works, and why its experiments are capable of exposing the deepest structure of reality. That is where we go next. To understand why the discoveries at CERN matter so much, it is important to understand what CERN was built to do and why no other scientific institution on Earth can do what it does. CERN, the European Organization for Nuclear Research, was created to answer one fundamental question: what is the universe made of at its most basic level? Not planets or stars, but the smallest components of matter itself. The idea is simple in theory but extraordinarily difficult in practice. If you can break matter down into its smallest parts and observe how those parts behave, you can uncover the rules that govern all of reality. This is why CERN built the Large Hadron Collider. It is the most powerful particle accelerator ever constructed. Hidden deep underground, it consists of a circular tunnel nearly 27 kilometers in circumference. Inside this tunnel, particles are accelerated to speeds extremely close to the speed of light and then smashed together with enormous energy. These collisions are not acts of destruction. They are acts of creation. When particles collide at such high energies, they briefly recreate the conditions that existed just after the Big Bang. For a fraction of a second, energy condenses into matter, producing rare particles that do not naturally exist under normal conditions. By observing these particles and how they decay, scientists can test their theories about the fundamental structure of reality. For decades, this approach worked exactly as expected. The Standard Model of particle physics predicted what particles should appear, how often they should appear, and how they should behave. Experiments at CERN and other laboratories around the world consistently confirmed these predictions. Each successful test strengthened confidence that humanity was on the right track. The crowning achievement of this effort came in 2012 with the discovery of the Higgs boson. Often called the God particle in popular media, the Higgs boson is responsible for giving other particles mass. Without it, matter as we know it could not exist. Its discovery confirmed a theory proposed nearly 50 years earlier and marked a major triumph for modern physics. At that moment, many physicists believed they were standing at the edge of a complete understanding of the universe at the smallest scales. The remaining questions seemed like details that would be filled in over time. What happened instead was unexpected. Once the Higgs boson was confirmed, CERN did not stop. The collider was upgraded to reach higher energies and produce more precise data. With each upgrade, scientists gained the ability to probe deeper into the structure of reality. And as they did, the data began to change. The experiments no longer simply confirmed existing theory. They began to test its limits. Particles were still behaving mostly as expected, but not perfectly. Small deviations appeared in decay rates, interaction strengths, and symmetry behaviors. At first, these differences were so minor that they were dismissed as statistical fluctuations. But as more data accumulated, the deviations remained. This is a critical point. In particle physics, random errors disappear as data increases. Real effects become clearer. What CERN scientists were seeing did not fade with time. It sharpened. This suggested that the experiments were no longer just measuring known physics. They were brushing against something new. Another important aspect of CERN's work is that experiments are now more precise than the theories used to interpret them. This is an unusual and uncomfortable situation for scientists. Traditionally, theory leads experiment. Equations predict outcomes, and experiments confirm them. At CERN, that relationship has begun to reverse. The detectors are now so sensitive that they can measure phenomena that existing models were never designed to explain. This creates a problem. When data does not match theory, scientists must decide whether to modify the theory or search for entirely new frameworks. This is not a small adjustment. Changing foundational physics is like rewriting the rules of a language while people are still speaking it. One of the reasons CERN is uniquely positioned to expose these problems is its scale. The energies involved in LHC collisions are far beyond anything naturally occurring on Earth. Only the most extreme cosmic events, such as supernovae or black hole environments, produce comparable conditions. By recreating these energies in a controlled setting, CERN allows scientists to study aspects of reality that are otherwise inaccessible. This also means that CERN operates in a regime where our everyday intuition completely fails. At these scales, particles can exist in multiple states at once, appear and disappear spontaneously, and interact through forces that do not behave in familiar ways. The deeper CERN probes, the stranger reality becomes. It is also important to understand what CERN is not. CERN is not designed to open portals, create black holes that threaten Earth, or manipulate reality in science fiction ways. The fears surrounding CERN often stem from misunderstanding. The real danger CERN poses is not physical destruction, but intellectual disruption. By pushing experiments into regimes where existing theories break down, CERN forces humanity to confront the possibility that our understanding of the universe is fundamentally incomplete. This is why the anomalies being observed are so significant. They are not failures of technology. They are signs that the universe may be governed by deeper rules that we have not yet discovered. In many ways, CERN has become a mirror. It reflects not just the behavior of particles, but the limits of human knowledge. The more powerful the collider becomes, the clearer those limits appear. This sets the stage for the most troubling aspect of CERN's findings, specific anomalies that directly challenge the standard model. These are not vague mysteries, but measurable, repeatable deviations that suggest something beyond known physics is influencing reality. To understand these anomalies, we need to look at the data itself and the specific problems that refuse to go away. That is where the idea of the crack becomes impossible to ignore. By the time scientists at CERN began speaking seriously about anomalies, the issue was no longer theoretical. It was no longer about abstract gaps in knowledge or unanswered questions. The problem had become measurable. Something in the data was refusing to behave the way the standard model said it should. To understand why this is so significant, it helps to understand how precise modern particle physics actually is. Predictions made by the standard model are often accurate to many decimal places. When experiments disagree with those predictions, even slightly, it sets off alarms. Physics is not forgiving of almost correct answers. The first category of anomalies involved particle decay. In simple terms, particles are not permanent objects. Many exist for only fractions of a second before transforming into other particles. The standard model predicts exactly how often these decays should occur and which particles should appear as a result. At CERN, some particles were decaying more frequently into certain products than expected, and less frequently into others. The differences were small but consistent. When researchers accounted for all known sources of error, the discrepancy remained. This suggested that an unknown influence might be affecting these decays. Something subtle, something not included in current models. Another anomaly involved symmetry. Symmetry is one of the deepest principles in physics. It states that the laws of nature should behave the same way under certain transformations, such as flipping spatial directions or exchanging particles with their antiparticles. The standard model relies heavily on these symmetries. However, some experiments indicated violations that were larger than expected. While symmetry breaking is not entirely new in physics, the patterns being observed did not fit existing explanations. The universe appeared to be favoring certain outcomes in ways that current theory could not fully justify. One of the most well-known examples of this problem is the behavior of muons. Muons are elementary particles similar to electrons, but much heavier. Because of their properties, muons are extremely useful for testing the limits of physics. They interact with known forces in very predictable ways, making them ideal probes for discovering new phenomena. When muons are placed in a magnetic field, they wobble, or precess, at a rate determined by their interactions with surrounding particles and forces. The standard model predicts this wobble with remarkable precision. But measurements showed that muons were wobbling slightly faster than expected. This difference, known as the muon G2 anomaly, persisted even after years of refinement and repeated experiments. The discrepancy was small, but statistically significant enough to suggest that unknown particles or forces might be influencing the muons. In physics, this is a serious problem. If muons are being affected by something unseen, it implies that there are particles or interactions beyond the standard model. This is not a minor adjustment. It means the current framework is incomplete. The situation becomes more troubling when multiple anomalies point in similar directions. It is one thing for a single experiment to disagree with theory. It is another when several independent measurements all suggest the presence of unknown physics. In addition to muon behavior, CERN experiments have observed unexpected patterns in how certain particles interact with each other. These interactions appear to violate a principle known as lepton universality, which states that all leptons should behave identically under the same conditions, except for differences due to mass. The data suggests that this principle may not hold perfectly. If confirmed, this would represent a fundamental flaw in one of the core assumptions of particle physics. At this point, physicists are faced with difficult choices. One option is that the anomalies will eventually disappear as more data is collected. Another is that subtle experimental errors remain undiscovered. But the most unsettling possibility is that the anomalies are real. If they are real, then the standard model is not just incomplete in an abstract sense. It is actively failing to describe nature under certain conditions. This leads to the concept of the crack. The crack is not a single discovery. It is the growing realization that multiple parts of the theoretical framework are under strain. Like a structure exposed to increasing pressure, weaknesses are appearing where none were expected. Importantly, this does not mean that all of physics is wrong. The standard model still works extremely well in most situations. But history shows that successful theories can still be fundamentally limited. Newtonian mechanics works perfectly for everyday motion, yet it breaks down at high speeds and strong gravitational fields. The anomalies at CERN may represent a similar boundary. They suggest that at extreme energies and precision, a deeper layer of reality becomes visible. A layer governed by rules we do not yet understand. This raises a critical question: what happens if we continue pushing deeper? As CERN increases collision energies and gathers more data, these anomalies may become clearer. They may reveal entirely new particles, forces, or dimensions of space. Or they may force physicists to abandon assumptions that have been taken for granted for decades. Either way, the implications are profound. If the standard model is incomplete, then our understanding of matter, energy, and the universe itself is only partial. This would affect not just physics, but cosmology, astrophysics, and our understanding of the origin and fate of the universe. The crack is not a failure. It is an opening. An opening into a deeper and more complex reality. To understand what that reality might look like, scientists must confront another disturbing idea, that the universe itself may be under stress, governed by principles that push it toward instability. That is where the story goes next. As the anomalies at CERN continue to accumulate, physicists were forced to confront a possibility that had long been uncomfortable to discuss. What if the problem was not just missing particles or undiscovered forces, but something more fundamental about reality itself? For most of modern physics, the universe has been treated as stable. Space and time form a reliable backdrop in which particles interact according to well-defined rules. Even when phenomena are strange, such as quantum uncertainty, the underlying structure is assumed to be consistent. But some of the data emerging from high-energy experiments suggests that this assumption may not always hold. According to Einstein's theory of relativity, space and time are woven together into a four-dimensional fabric that can bend and curve under the influence of mass and energy. This framework has been confirmed repeatedly through observations of gravitational waves, black holes, and cosmic expansion. However, when relativity is combined with quantum mechanics, serious problems arise. At extremely small scales, space-time appears to lose its smooth structure. Quantum fluctuations cause violent distortions, making it impossible to define precise distances or durations. Attempts to describe gravity at the quantum level result in mathematical infinities that cannot be resolved. This breakdown suggests that space-time may not be fundamental. Instead, it may be an emergent phenomenon, arising from deeper processes that only become visible at extreme energies. CERN operates closer to these energies than any other laboratory on Earth. Some physicists suspect that the anomalies observed in particle behavior are indirect signs of this deeper structure. If space-time itself has limits, then pushing particles to extreme energies could reveal deviations from expected behavior. This would mean that the crack is not located within particles, but within the stage on which particles exist. The idea that space-time might have a granular or discrete structure is not new. Various theories propose that at the smallest scales, space-time is composed of fundamental units, similar to pixels on a screen. Under normal conditions, this structure would be invisible. But under extreme stress, its limitations might become apparent. If this is true, then some of the anomalies seen at CERN could be symptoms of spacetime reaching its resolution limit. Another possibility is that reality is governed by multiple overlapping layers of rules, each dominant at different scales. At everyday energies, classical physics applies. At atomic scales, quantum mechanics dominates. At cosmic scales, relativity governs behavior. The problem is that these frameworks do not merge cleanly. CERN operates in a regime where these layers overlap. Quantum effects, relativistic effects, and extreme energies collide in ways that expose contradictions. The cracks appear where these frameworks fail to align. This perspective suggests that the universe is not broken, but compartmentalized. Each theory works within its own domain, but no single framework fully explains reality at all scales. The stress CERN places on these boundaries is intentional. By pushing particles to higher energies and measuring their behavior with unprecedented precision, scientists are deliberately probing the limits of known physics. What they are discovering is not chaos, but resistance. Reality appears to resist simplification. Each time physicists attempt to unify forces or eliminate inconsistencies, new complexities emerge. The deeper they look, the more layered and intricate the universe appears to be. This realization has significant implications. It suggests that a final, simple theory of everything may not exist in the form once imagined. Instead, reality may be governed by a hierarchy of principles, each emerging from deeper levels. The anomalies at CERN are forcing physicists to reconsider their assumptions about what constitutes a fundamental explanation. They are revealing that our current theories may be approximations, valid only within certain limits. And those limits are now being reached. If reality is under stress at the deepest levels, then the next question becomes unavoidable: what are we missing? What components of the universe remain invisible, and how much of reality operates beyond our ability to detect it? To answer that, scientists must confront the largest missing piece of all. That brings us to what we do not see, but know must exist. As physicists grapple with the possibility that reality itself is under strain, another question becomes impossible to ignore. What if the anomalies observed at CERN are not signs of instability, but evidence of something vast and unseen? Modern physics already accepts that most of the universe is invisible. When astronomers measure the motion of galaxies, they find that visible matter alone cannot explain what they see. Stars orbit too fast. Galaxies hold together when they should fly apart. Entire clusters behave as if enormous amounts of unseen mass are present. This unseen mass is called dark matter. Dark matter does not emit light, absorb light, or interact with electromagnetic radiation in any detectable way. Its presence is inferred only through its gravitational effects. Based on current estimates, dark matter makes up roughly 85% of all matter in the universe. This means everything we can see, stars, planets, gas, dust, and life itself, accounts for only a small fraction of what actually exists. For decades, physicists believed dark matter was composed of unknown particles that simply had not yet been detected. The Large Hadron Collider was expected to produce these particles under the right conditions. If dark matter interacted even weakly with known forces, CERN should have seen signs of it. But so far, it has not. Despite years of increasingly sensitive experiments, dark matter has remained stubbornly absent. No clear signals. No unmistakable tracks. No definitive interactions. This absence is troubling. If dark matter is not showing up where theory predicts it should, then either it behaves in ways we do not understand, or it is not made of particles in the conventional sense at all. This has forced physicists to reconsider fundamental assumptions. One possibility is that dark matter interacts through forces entirely unknown to us. forces that do not couple to the standard model in detectable ways. If so, the anomalies seen at CERN could be indirect effects of these hidden interactions. Another possibility is that dark matter is not matter in the traditional sense. It could be a manifestation of deeper structure within spacetime itself, altering gravity without requiring new particles. These ideas were once considered fringe. Now, they are actively explored. The failure to detect dark matter has also renewed interest in theories involving extra dimensions. Some models propose that our universe exists within a higher dimensional space. While we experience only 3 dimensions of space and 1 of time, additional dimensions could be compactified or hidden at extremely small scales. If such dimensions exist, particles could move through them in ways we cannot observe directly. Energy might appear to vanish from our universe, when in reality it is leaking into another dimension. This would explain several puzzling observations. It could account for missing energy in particle collisions. It could explain deviations in particle decay rates. It could even provide a natural explanation for dark matter. CERN experiments are uniquely positioned to test these ideas. High-energy collisions could produce signatures of extra dimensions, such as unexpected particle jets or missing momentum. So far, no definitive evidence has been found. But again, the absence of confirmation does not eliminate the possibility. It suggests that if extra dimensions exist, they may be more subtle than originally imagined. This brings us to a more unsettling idea. What if the anomalies at CERN are not pointing toward new objects, but toward new limits? Some physicists have begun to question whether reality itself has a finite resolution. Whether there is a smallest unit of space, time, or information beyond which physics cannot be meaningfully defined. In this view, the universe is not infinitely divisible. At extreme scales, the smooth mathematical structures we rely on break down. The laws of physics become approximations, not exact descriptions. This perspective aligns with ideas from information theory and computational physics. It suggests that the universe may process information in discrete steps, similar to a computation. If this is true, then pushing experiments beyond certain thresholds could reveal inconsistencies not because new particles exist, but because the underlying framework cannot support infinite precision. This leads some physicists to entertain the idea that reality may be constrained by deeper informational rules. The concept of a simulated universe often arises in this context, not as a claim of artificial design, but as a way of exploring the implications of finite information capacity. In such a universe, anomalies could emerge when systems are pushed beyond their designed resolution. While this idea remains speculative, it is taken seriously enough to be discussed in peer-reviewed literature. What connects all of these possibilities is a shared conclusion: the universe is far more complex than the models we currently use to describe it. Whether the missing piece is dark matter, hidden dimensions, unknown forces, or fundamental limits on information, the result is the same. Our current understanding captures only a small portion of reality. The anomalies at CERN are not random. They are clues. Clues that point towards something large, hidden, and deeply connected to the structure of the universe. As physicists attempt to follow these clues, they are confronted with another challenge. The deeper the mystery, the greater the responsibility that comes with uncovering it. Because discovering the missing pieces of reality does not only expand knowledge. It changes how humanity understands its place in the universe. And that brings us to the human side of this story. As the implications of CERN's findings become clearer, it is easy to focus entirely on equations, particles, and abstract theories. But behind every experiment, every data set, and every anomaly, there are people. And those people are beginning to feel the weight of what they may be uncovering. Physicists are trained to be cautious, skeptical, and precise. They are not prone to panic or exaggeration. When something does not fit existing theory, the default reaction is not excitement, but restraint. Results are questioned relentlessly. Assumptions are challenged. Alternative explanations are explored. Yet the current situation has created an unusual atmosphere within the scientific community. There is a growing sense of unease. This unease does not come from a fear of immediate danger, but from a deeper realization. The tools physicists rely on to interpret reality may no longer be sufficient. The language of physics itself may need to change. Historically, moments like this are rare. Most scientists spend their careers refining existing theories rather than overturning them. A major paradigm shift happens perhaps once in a generation, sometimes once in a century. When it does, it disrupts not only science, but culture, philosophy, and technology. The anomalies at CERN suggest that such a shift may be approaching. This creates a difficult psychological tension. On one hand, discovering new physics is the ultimate goal of fundamental research. On the other hand, the implications of that discovery may be vast and unpredictable. Some scientists worry about what lies beyond the standard model not because it is dangerous, but because it is unknown. Unknown physics means unknown consequences. When humanity learned how to harness nuclear energy, the discovery brought both progress and destruction. The same equations that power cities also created weapons capable of annihilating them. That duality is never far from the minds of researchers working at the frontier of knowledge. While CERN's work is not directly comparable to nuclear weapons, the lesson remains relevant. Fundamental discoveries often lead to technologies that reshape civilization in ways no one can fully anticipate. This awareness has led to ethical discussions within the scientific community. Should there be limits to how far experiments are pushed? Who decides which questions are safe to ask? Is there a responsibility to slow down when understanding lags behind capability? These are not easy questions. CERN operates under strict international oversight, with safety protocols and ethical reviews built into its structure. Yet ethics in science is not just about physical safety. It is about knowledge itself. Once something is discovered, it cannot be undiscovered. Another source of tension comes from disagreement among scientists. The anomalies observed at CERN are interpreted differently depending on theoretical perspective. Some researchers believe the results will eventually align with existing models. Others are convinced that new physics is already revealing itself. This division is natural, but it also highlights uncertainty. When experts disagree at the deepest levels, it signals that the foundations of the field are being tested. For younger scientists, this moment is both exciting and daunting. Entire careers may be shaped by how these questions are resolved. For more established physicists, the possibility that decades of work may need revision is emotionally challenging. Science is often portrayed as purely objective, but scientists are human. They invest years of effort, identity, and belief into their work. A major shift in understanding can feel like the ground moving beneath their feet. Public perception adds another layer of pressure. CERN has long been the subject of speculation and fear. Misunderstandings about black holes, alternate realities, and cosmic disasters circulate widely online. While scientists dismiss these fears as unfounded, they are aware that public trust is fragile. Communicating uncertainty without fueling panic is a delicate balance. Too much caution can look like secrecy. Too much openness can be misinterpreted. This is one reason CERN tends to speak carefully and incrementally. The goal is clarity, not drama. Still, the emotional impact of working at the edge of knowledge is real. When experiments begin to challenge the deepest assumptions about reality, it forces scientists to confront questions that are not purely technical. Questions about meaning, about limits, about humanity's role in the universe. For centuries, science has steadily removed humanity from the center of the cosmic story. Earth is not the center of the universe. The sun is one star among billions. Our galaxy is one among trillions. Now, physics may be delivering another humbling message. Reality is not obligated to make sense to us. The discomfort this creates is not a weakness. It is a sign that science is doing what it does best, challenging certainty. As physicists continue to analyze data and refine experiments, they are acutely aware that they may be standing at the edge of a profound transformation in human knowledge. The question is no longer just what the universe is made of. It is whether humanity is prepared for what it might discover next. Because once the foundations of reality are questioned, nothing built upon them remains untouched. This brings us to the broader implications of CERN's findings, beyond laboratories and equations, and into the way we understand existence itself. Up to this point, we have explored the anomalies, the cracks in our understanding, and the unease among scientists. But now we reach the most profound question: what do these discoveries mean for reality itself? If the standard model of particle physics is incomplete, then everything built upon it is also provisional. Chemistry, astrophysics, and cosmology all rely on these foundational principles. For most practical purposes, the current models work extremely well. Cars drive, airplanes fly, stars burn, and planets orbit as predicted. But at the deepest levels, the universe may be operating according to rules we barely understand. One way to think about it is to imagine a machine. On the outside, it appears to function perfectly. But inside, gears may be missing, spinning differently, or influenced by forces no one anticipated. The machine still works, but its inner workings are not fully understood. This is where humanity currently stands with the universe. The implications of this are staggering. If our theories are incomplete, then the universe could behave differently under extreme conditions than we currently expect. Black holes, neutron stars, the very birth of the universe, or even the eventual fate of all matter might not follow the patterns predicted by existing physics. It also raises questions about determinism. Science has long operated under the assumption that if the rules are known, outcomes are predictable, at least in principle. If these rules are only approximations, then predictability itself may be limited. Certain events in the universe might not follow neat, mathematical paths. The boundary between what is possible and impossible may be more fluid than previously believed. Another consequence relates to the concept of constants in physics. Fundamental constants, like the speed of light, the gravitational constant, or the charge of the electron, are assumed to be fixed throughout the universe. They are the invisible scaffolding upon which all physical laws rest. Yet some speculative theories suggest that if the standard model is incomplete, these constants may not be as absolute as we think. Small variations could exist under extreme conditions, in distant parts of the universe, or at earlier moments in cosmic history. This perspective forces a reconsideration of what we mean by laws of nature. Are they fixed rules, or emergent patterns that arise under certain conditions? Are they universal, or local? The anomalies observed at CERN suggest that we may only be scratching the surface of these questions. The potential for a new physics also opens the door to phenomena that, until now, have been relegated to theory. Extra dimensions, hidden forces, and new particles may exist, influencing reality in ways we have never directly observed. Some of these elements could explain dark matter, the accelerating expansion of the universe, or even the behavior of gravity at the smallest scales. In addition, the cracks in current models have philosophical implications. If the universe is not entirely deterministic, or if reality is layered in ways we cannot perceive, then our understanding of cause and effect, of time, and even of existence itself becomes more complex. Observers may influence outcomes in ways more profound than previously believed. The line between observer and universe may blur at extreme scales. The idea that our comprehension is limited is not new. Throughout history, science has steadily revealed layers of reality previously hidden. The discovery of atoms, the theory of relativity, and quantum mechanics all demonstrated that everyday intuition is insufficient for understanding the universe. Each of these breakthroughs forced humanity to accept that the cosmos is stranger than it appears. CERN's anomalies may represent the next such moment. This is not about science fiction or speculation for entertainment. This is about real, measurable phenomena that refuse to fit into current frameworks. The cracks in our understanding are not a warning about imminent danger, they are an invitation to explore deeper truths. These truths could fundamentally reshape the way we approach technology, cosmology, and even the concept of life itself. Imagine a universe where hidden dimensions influence the forces around us, where energy behaves differently than expected, or where unseen matter governs the motion of stars. The potential applications of understanding such phenomena are immense, even if they are centuries away. Yet perhaps the most profound implication is philosophical. If reality is more complex than we have assumed, then everything we consider fundamental, space, time, matter, and energy, may be emergent properties of deeper processes. The universe may be less a collection of things and more a dynamic system, operating according to principles we are only beginning to glimpse. This realization challenges our perception of certainty. Humans are creatures who seek patterns, predictability, and control. The cracks revealed by CERN show that the universe does not guarantee these comforts. Knowledge, it seems, comes with the understanding that some mysteries may always lie beyond our reach. And yet, these cracks are also opportunities. They are openings into deeper understanding, gateways to discoveries that could redefine science, philosophy, and our place in the cosmos. Every anomaly, every unexplained result, is a signpost pointing toward truths we have not yet encountered. As we move forward, the challenge is not only scientific but existential. How will humanity integrate a universe that is stranger, deeper, and more layered than we have ever imagined? The answer remains unknown, but the search has begun. Ultimately, the cracks in our understanding are not weaknesses, they are invitations. They ask us to question, explore, and expand the boundaries of knowledge. The universe is far more complex than we realize, and CERN is providing humanity with its first glimpses beyond the veil. What we do with that knowledge may define the future of science, and of civilization itself. As we reach the final act of this journey, it is worth stepping back to consider the full scope of what CERN's discoveries might mean, not just for physics, but for our understanding of existence itself. The anomalies, the cracks, the unexplained deviations, all of them point to a simple but profound truth: reality is far more complex than we imagine. The universe we experience in daily life, the laws that govern chemistry, electricity, and motion, are only part of a far deeper structure. Beyond the familiar, there may be layers of reality operating under rules we have yet to comprehend. These are not easy questions. They challenge not only science but philosophy, metaphysics, and our place in the cosmos. Yet they are questions worth asking, because the pursuit of knowledge itself has been humanity's greatest achievement. As we continue to explore, the work at CERN reminds us that science is not just about answers, it is about curiosity, rigor, and the courage to confront uncertainty. Every particle collision, every new measurement, every anomaly is a step further into the unknown. The universe is not obligated to make sense to us, but it is generous in the clues it leaves behind for those willing to look. The future of physics may not bring simple, definitive answers. It may reveal a universe more layered, complex, and mysterious than we have ever imagined. But this is precisely what makes the pursuit worthwhile. Each crack is not a warning, but an invitation. Each anomaly is a signpost pointing toward truths humanity has not yet uncovered. Perhaps the ultimate lesson is this: reality is not static. It is dynamic, intricate, and often surprising. Humanity's understanding of it is provisional, constantly evolving. What we consider solid and fundamental today may be revealed as emergent tomorrow. And yet, with patience, rigor, and imagination, we can continue to push the boundaries of knowledge, illuminating the hidden structures that govern existence. In the end, the discoveries at CERN remind us of our place in the cosmos, not at its center, but as explorers navigating the edges of understanding. We may never grasp the full complexity of reality, but every anomaly, every crack, every unexplained result brings us closer to the universe's ultimate truths. The universe, it seems, is both stranger and more magnificent than we have imagined. And the journey to uncover its secrets has only just begun.